Hello, good morning, and welcome to the fourth and last day of Italy. Today, we're going to start with Jared Ducker Lichtman from Stanford and Mathink, and he will talk about Gauss and an agentic formalization of the prime number theorem. Please, Jared.
Well, thank you to the organizers and everybody for the opportunity to speak today. Can everyone hear me okay? Is the volume okay?
Yes, we can hear you.
Okay, great. Thank you so much. Yeah, so today I'd like to talk a little bit about the prime number theorem. So I know many people in the audience may not be number theorists, so I want to maybe spend a bit of time explaining what the problem is and some of its maybe historical context. Um, and more recently, the initiative to formalize the prime number theorem that was led by Terry Tao and Alex Kontorovich, and in particular highlight some of the recent results using Gauss, which is a new agent for formalization. And time permitting, I know maybe it's a bit of a tight schedule. I could say a word about maybe what mathematics will start to look like in the future. So maybe one way to interpret the historical events was that in the 1790s, a young lad named Gauss noticed that the prime numbers seemed to become more and more rare the further out along the number line that numbers got. And he was looking at these, for the time, quite long list of tables of numbers and seeing the kind of sparsity of primes for the larger and larger numbers. But in reality, maybe by modern day sizes, he was really looking at a very relatively small table. And maybe you'd say today he was determining from a very kind of small training set, from a small data set, that he observed this remarkable trend that on average, if you looked at numbers of size x, then there was a probability about 1 in the natural logarithm of x chance that that number was prime. And in modern kind of language, this kind of spurred a lot of interest and got formulated in a more precise way in what became known as the prime number theorem, which now we would consider it a series of primes up to x, actually prime powers up to x, and we'd weight each prime power by log p to account for the kind of natural logarithmic weighting of primes. And we define this function, psi of x, which is called the Chebyshev psi function. And the modern formulation of the prime number theorem is the assertion that psi of x grows asymptotically like x. So in other words, this confirms that the primes have this kind of 1 over the logarithm density on average. And since the prime number theorem was formulated, this spurred a lot of work in the 1800s to prove the conjecture, developing a lot of tools, in particular in analysis. And the proof was eventually obtained by Adamard and Develay-Poussin in 1896, in which they obtained a precise formula for the Chebyshev psi function, namely that psi of x is equal to x as a main term, which they expect, and producing an error term of the form x over e to a constant over the square root of log x. So this is an expression maybe that comes up a lot in analytic number theory, but maybe to those who are not initiated, this expression is saying that it is some function which is growing much more slowly than x. In particular, it's less than x over log x to the 100th power. It's growing slow. It's a lot smaller than x over any power of log, and yet it's actually bigger than let's say x to the 0.099. So it's bigger than any fractional power of x, but it's smaller than a logarithmic savings. And the key ingredient that was used to prove this classic version of the prime number theorem is what's known as the zero-free region for the Riemann zeta function. So the Riemann zeta function is perhaps one of the most famous functions in all mathematics, and in their proof, they showed that this function is never zero in a particular region of the complex plane. So the Riemann zeta function takes in a complex number as input and outputs a complex number. And the key to the proof of the prime number theorem is that this function never vanishes when the input of, let's say s, call it as a variable, that the real part of the input is always kind of larger than 1 or maybe a bit less. So that the real part of s is bigger than 1 minus a constant over the logarithm of the imaginary part of s. And one can imagine a statement like this in various strengths. And this also brings us to the question of the Riemann hypothesis. But this was the precise formulation, this so-called classical zero-free region for the zeta function. And this classic result actually built on a lot of revolutionary ideas of Riemann himself, which was introduced in his famous 1859 paper. So Riemann, by training, was a geometer and did most of his work giving foundations for differential geometry. But he wrote a single paper in number theory, which was in 1859, which is 8 pages long, in which he formulated a connection between the distribution of prime numbers and a specific function of a complex variable, namely the Riemann zeta function, and in which he also formulated the Riemann hypothesis. So in one single paper, he essentially lit up the field of number theory and kind of dropped the mic and left with that one paper. But really, this result was a culminating, so the prime number theorem should be viewed as really a culminating achievement of, we should say, 19th century mathematics, making use of cutting-edge techniques from, at the time, this new field of complex analysis. So, as I mentioned, this question is intimately tied up with the Riemann hypothesis, which is the statement that the zeros of the zeta function should all occur, or at least the non-trivial zeros of the zeta function, should all occur on the line of the real part of s is equal to 1/2. And Riemann was motivated to make this conjecture because of this deep relationship that he identified between the distribution of prime numbers and the location of the zeros of the zeta function. And in particular, if one of the reasons why the Riemann hypothesis is such a sought-after result is that if it's true, then this would imply that we have a very precise understanding of the distribution of prime numbers. So in particular, this would tell us that our function psi, the Chebyshev psi function, grows like x as a main term as before, but now has essentially the square root of x as an error term. So this shows very kind of strong convergence to the main term. And this evokes the idea of even like a Gaussian or a normal distribution for kind of a rate of convergence to a mean. So this was the kind of highlight of the 19th century. In the 20th century, it was believed that this result was that the prime number theorem was very sophisticated in the sense that any proof of it must require complex analysis. And maybe this will be interesting coming up till today, but it became a dogma kind of espoused by G.H. Hardy that any proof must require complex analysis. And so it was a great shock to the number theory community when in 1949, Selberg and Erdős proved that the prime number theorem could be shown using elementary tools, so without using complex analysis. And in particular, their so-called weak form of the prime number theorem showed that psi of x grows like x as a main term again, but now plus little o of x, so some error term which is smaller than x tending to 0 divided by x, but with some unspecified qualitative rate of decay. So this is weak in this qualitative sense. So this kind of progression of going from strong results using complex analysis then weaker results using kind of more elementary methods kind of motivates a lot of the discussion for the much more recent developments about now relating to formalization. Because now about 2 years ago, in January of 2024, Terry Tao and Alex Kontorovich announced a project to formalize the prime number theorem in Lean. I think maybe Alex also spoke about the P&T plus project in his talk. And they had an exciting update on that project in July of 2025, in which Alex and Terry announced that they proved a so-called medium version of the prime number theorem. And they had displayed this nice dependency graph identifying the results they had proven, as well as some of the remaining challenges on the roadmap. And I guess Alex coined the term of the so-called medium prime number theorem because it was in between the level of difficulty between maybe the strong classical prime number theorem with the error term and the weak elementary version of the prime number theorem of Selborg and Erdős, because they had obtained this error term of x to the e to the minus kind of log x to the 1/10th power. And so the difference between the classical strong prime number theorem and this medium prime number theorem is this exponent in the logarithm of 1/10 as opposed to 1/2. And it turns out that in many applications in number theory, for the reason why people use the prime number theorem, this medium strength result was actually good enough to get many of the desired corollaries. But part of the reason for doing this result was that it kind of avoided some of the core difficulties that arose in complex analysis in order to prove this classical zero-free region for the Riemann zeta function. And when this result was announced, I thought this was a very exciting, just in general as a result. I'd heard, I think maybe even 2 years ago, that they really quickly, maybe in about a month, they had proven in Lean the elementary estimate for the prime number theorem, the weak prime number theorem. But then maybe it was more challenging to prove the strong result. And I think over time, I think maybe it even been a sense that complex analysis is one of these fields which might need more effort. And so with that as context, we decided that it would be a very great opportunity to actually dig into the complex analysis itself. And over the summer, since their announcement, we worked in developing an agent for formalization, which we call Gauss, which was able to take human, the kind of a classical proof of the zero-free region and translate that into Lean using Gauss. And this process, which I guess the project which up to that point had taken about 18 months, we were able to complete the core complex analytic component in a 3-week time span. So along the way, so in addition to getting the strong form of the prime number theorem, this classical version, I would also regard the kind of one of the kind of main contributions is actually proving some kind of key missing results from the library that could be useful for future initiatives that use complex analysis in its results. And for people who are interested, the proof of the formal proof in Lean is available on GitHub. So maybe just to kind of give a rough picture of what the kind of workflow looked like for interacting with maybe a formal assistant. In the case of the prime number theorem, we took the classical textbook version of the zero-free region for the Riemann zeta function, and with my, in this case, an expert number theory assistant, expanded these kind of terse proof from, let's say, a textbook, and filled in extra details that would be useful for an automated agent. And this was relying on the standard kind of natural language blueprint that's kind of used in GitHub, and provided some additional scaffolding. And using that kind of LaTeX, maybe extra annotations on the LaTeX, getting fed into the agent, Gauss was able to kind of input and, in a sequence of steps, formalize the proof. So the maybe a kind of rough workflow to keep in mind at the time is we would feed first the statements, for example, of theorems, lemmas, sometimes definitions, and Gauss would propose candidate statements that would satisfy this informal version. And it was actually quite easy, maybe in the matter of seconds to minutes, for Gauss to produce candidate statements. And I would regard that the statements themselves were guaranteed to compile. So this is an aspect of verification. But then there's the question of, does that statement correspond semantically to the underlying mathematics that we cared about? And so that's where kind of human oversight came in to validate the interpretation of that statement. And once the statements are validated by a human to be correct, then they become the goals for Gauss to then autonomously start working on producing the proofs using the using the LaTeX blueprint as a kind of a scaffold for giving hints on how to proceed in the proof. And so the way it's structured is there was a number of lemmas for a given run. And over time, Gauss, maybe over the course of an hour or several hours, would start producing more proofs of these lemmas. And at least in the case of the prime number theorem, we got into a good rhythm where on a given batch, I would say probably half the lemmas would be produced in the first couple hours. And then there would be a long tail of lemmas that would kind of trickle in over the rest of the day, sometimes even a little bit longer than a day, leaving, I would say, about 90 to 95% of the lemmas completed, with a long tail of maybe 5 to 10% of lemma statements, which Gauss was unable to prove. And then we'd iterate this process in which we take those most difficult 5 to 10% of lemmas and then further expand, with human oversight, the blueprint into subsequent lemmas and decompose them for then Gauss to run on a subsequent iteration. And so this, at the time, involved a very intensive 3-week span on my part of very almost like working on a research problem with a collaborator where you're both working all hours of the day and night. And I think it was a very kind of exhilarating glimpse of what maybe a future kind of human-machine interaction could be. But also, I would say that moving forward, the level of granularity and the level of automation that can be used in Gauss and future agents, I think will be more closer to what maybe a human level of proof style would be, so that it might be less granularly intensive, but become more of a kind of natural, seamless interaction. And I'm personally very excited about what the future of this space looks like. And now there's, I think, a lot more excitement just more broadly in the community about what these kinds of interactions could look like. So I want to say now maybe a bit about what the artifact that we produced from the prime number theorem, this formal artifact. So given the human LaTeX input, Gauss autonomously produced all the formal code itself in about 25,000 lines of lean code. And that comprised about 1,000 theorems and definitions. And here we can see kind of a dependency graph of all these lemmas and definitions. And maybe it's worth noting that formal proofs at this scale of about 25,000 lines have historically been major milestones, which have often been the culmination of multi-year efforts by kind of groups of humans working together. And one of the kind of, I think, exciting features is that now we might have the opportunity to be more ambitious on trying to work on larger scale projects, even collaborating on pieces that people aren't necessarily coordinated with. And so to maybe contextualize the kind of progression of Gauss, at my first conference that was in this kind of really exciting area of formalization, there was a conference at Cambridge in June, the Big Proof Conference, in which we announced a prototype of Gauss, which had produced in about 3,500 lines of code for a result about the ABC conjecture on average. And that code was itself about an order of magnitude larger than previous automated efforts. So if you think about, for example, competition math problems, a solution to such a problem might be a few hundred lines of code, maybe for problems for like the IMO or something. And so we've, I think, starting to see some accelerating scale of what projects people can start to work on. And maybe for some context historically that I was interested to look up kind of more recently was that the largest formalization projects that have been accomplished, themselves these career-defining efforts that span over decades, were only about maybe an order of magnitude larger than 25,000 lines, so at maybe about 300 to 500,000 lines of code. Think about examples like the Kepler conjecture or the odd order theorem for groups. These massive collaborations produced artifacts of code which is about 500,000 lines. And even taking maybe an order of magnitude larger, if we look at, for example, Lean's MathLib, the kind of standard mathematical library, that's only maybe about an order of magnitude larger in turn. So its MathLib is about 2 million lines of code, and it comprises about 350,000 theorems and definitions, which had been, developed as a community by hundreds of human contributors over the span of about 8 years. And one of the kind of exciting aspects about this project is that it will be maybe an opportunity for more kind of collaboration with less technical knowledge required. So one, I think, exciting feature to me as a number theorist or as an analytic number theorist has to do with what Emily Riel talks about is so-called invisible mathematics. So this is the parts of proofs in a result that are required but are not mentioned in the proof because maybe they're seen as obvious, or maybe they're kind of something that people don't even acknowledge because it's kind of in the water that people are swimming in. But one of these kind of instances really kind of cropped up in the course of this project where the invisible mathematics really reared its head. And so I wanted to kind of mention this example. So in the course of proving the prime number theorem, and in the course of proving the classical zero-free region for the zeta function, one of the key results that we needed from complex analysis is the so-called Borel-Kara-Theodori theorem. So this has a technical statement. So it says that we have two radii, little r and big R, between 0 and 1, and we have a function defined on the disk of radius big R, an analytic function, so this nice analytic function, and we assume that the real part of the output of the function is always bounded by some constant m on when the input is from a smaller disk of radius little r. So we have this technical assumption on this nice function on how it behaves on two disks of two radii. And the statement is that we can take the bound on the real part of f and deduce a bound on the absolute value of f. So f of z is bounded by at most 2 little r over big R minus little r times m. So maybe this is a mouthful, but maybe to kind of interpret this statement more qualitatively, this statement is saying that we have some function, and if we have control over its real part, then we have control over its absolute value. And we know that the absolute value is essentially the square root of the real part squared plus the imaginary part squared. So this statement is saying that if we have control over the real part of f, then we also have control over the imaginary part of f. And so this is actually a very important critical statement in complex analysis. And actually using, for example, Cauchy's theorem, one can actually deduce that you actually get control over the absolute value of the derivative simultaneously, maybe up to a different constant depending on the radii. But this kind of technical statement turns out to be one of the key inputs that goes into the zero-free region for the zeta function. And this was one of the main technical lemmas that was identified by Alex for the proof. And the key idea is that in the prime number theorem, we want to apply this Borel-Cathodori theorem in the case where the function f we choose is the logarithm of the zeta function. And one of the important things to note is, or one of the main motivations for the field of complex analysis in general, is really to motivate the idea of what it means to take the logarithm of a complex number. So we know what the logarithm of a real positive number is. Taking the logarithm of a negative number, this is strictly forbidden because we run into issues. And it turns out if you use like analytic continuation, there's a way to kind of make a branch cut along the negative real axis and extend the logarithm to the complex plane outside of this branch cut. But even in the standard way of doing this, the branch cut, you need to know that the function, so if you're taking the logarithm of a function, you need to know that that function is never 0 on the branch cut. However, we know already that the zeta function has trivial zeros already on this kind of negative real axis, so this kind of rules it out. So the standard kind of proof you would think using kind of even to define the logarithm breaks down, and one needs to actually use a different proof using a different branch cut to really make sure that the proof goes through. And nowhere in the proof of any analytic in any analytic number theory textbook does it mention that you actually are, number one, defining the logarithm and that you're using an alternate branch cut. You don't even kind of mention that. You just say you take the logarithm. So we were forced to prove a lot of these basic theorems, and even to, for example, to define that there is a branch cut for a logarithm, we needed to prove this very basic result that an analytic function has an antiderivative, and therefore you can take a complex logarithm. And so this was some examples of these invisible mathematics really rearing its head, and then forcing maybe in the last week to really revise the informal LaTeX blueprint and add detail to accommodate this new kind of mathematical reality. And another kind of aspect of the project that I wanted to mention is the amount of kind of infrastructure that was required for operating these agents. So key infrastructure was provided at the time using these so-called Trinity environments developed in partnership with Morph Labs, in which agents, think of instances of Gauss, were each operating in their own lean kind of environment, which had to be verified. And this poses a serious engineering challenge for complex systems. And you can think of having thousands of concurrent agents, each with its own lean runtime, and using kind of terabytes of clusters of memory. So this is a strong infrastructure challenge in which the infinite branch technology in Morph Cloud was definitely critical to this functioning of the project. And so we're currently in beta testing for making this style of operation work for more broadly across the public. And in the moment, we're currently working with an initial group of mathematicians on their projects to kind of make this more accessible. And if you're interested, please kind of register with us for Gauss early access or potential career opportunities. And especially if you have an ambitious project that you think would be suitable to try out. And I just want to kind of maybe highlight in kind of at a high level is that this result maybe I think represents one of the first indications that we can maybe try to have formalization projects that operate at a larger and more industrial scale using tools from the community. And with additional kind of compute and algorithmic improvements, we're aiming to maybe contribute with the community orders of magnitude more formal code to the Lean repository over the next year. And so this is something, especially with the other exciting projects mentioned at this conference, I think we're starting to really see an opportunity for many people across the world actually getting very engaged with participating in kind of growing mathematics, the kind of surface area of all of mathematics. And in maybe the last minutes of the talk, I'd like to maybe say a word about maybe where I think maybe at a conceptual level where this project, kind of this larger project of the community might be heading towards. So maybe going maybe on a philosophical level a little bit, I wanted to maybe kind of frame this kind of project as an instance of a larger goal or a larger activity of mathematics, as viewing mathematics as a large knowledge base. So maybe one of the most ancient knowledge bases that we have, one which has been accumulated throughout human history, going back to maybe ancient Greece, where you have for example, the Pythagorean theorem. Once it's proven, it's permanent in its truth and can be used for forevermore. So each proof becomes available for future use. And up until maybe the past decades, this knowledge base has been represented in human natural language, sometimes even orally, but then maybe written down over the centuries into journals and textbooks and so on. But now I think we're at a moment where we're starting to see that this human knowledge base is getting formalized and more getting into a kind of compiling formal database. And we can see these kind of hypergraphs and the dependency graphs of these theorems, these definitions, and these conjectures, where the edges kind of are encoding these logical implications. This is maybe an instance of we're starting to see this maybe wave of more big data style of operation. And I would argue that whether in human kind of informal form or in more machine code form, the two objectives in the activity of mathematics has always been in expansion of the knowledge graph, of the knowledge base, or in compression of the knowledge base. And I would say that it's important to note that these two objectives are in tension by nature, but they also, I guess, help reinforce each other in that by expansion, I mean that we're always trying to add new theorems and new results to the database to build out what is true, what we know to be correct. And moreover, we're interested particularly in those statements and theorems that have kind of influence and causal relationships to other pre-existing entries in the database. So, for example, the Lichtman hypothesis is such a sought-after result because it has, if it's included and known to be true, it has so many downstream implications. There are many papers and hundreds of papers and textbooks written, assume the Riemann hypothesis, and then the following is true. And so we're also particularly interested more generally in identifying statements and results whose inclusion would actually have many downstream implications on the existing knowledge base. And so this is the idea of expansion. And dually, we're interested in the idea of compression by taking, for example, a given proof of a theorem and maybe writing it in fewer lines. That's the idea of golfing code. But also thinking about and so in the activity of golfing code, you can try to come up with tactics or other ideas for basic efficiency to reduce the number of lines of code. But another maybe kind of more meta level idea of compression is really maybe synthesizing and refactoring code bases. So maybe not a particular theorem or result, but maybe the code base as a whole is more compressed and has fewer lines. And one maybe at an informal level kind of concept of compression goes in the idea of abstraction, or coming up with important and deep definitions that really capture some mathematical phenomenon and that can unify many results across multiple domains. And the kind of recurring example is always Grothendieck, whose notions of schemes and sheaves really revolutionized geometry and could be really thought of as like refactoring the code bases of algebra, topology, and geometry to really have a kind of streamlined and compressed knowledge base that could then in turn lead to new results. So this activity I think is really fundamental, and I would argue that these two activities are essentially graph properties. These are intrinsic to the structure of mathematics itself, and I would view that these objectives would remain invariant whether human or machine are participating in this the activity of mathematics. Sometimes or often people would mention the idea of having kind of subjectivity, or the idea of some perception of beauty, or differing weightings of importance to particular results. And I could think that this idea of subjectivity could more relate to the idea of a relative property. So relative to the entire knowledge base of mathematics, or that what all humans have produced so far, any particular human being would only have a small fraction of this subgraph of this entire knowledge base. And the coherence and the kind of compact form that particular subgraph contains, as it's embedded in the larger graph, could maybe account for some of the subjective differing perceptions. And one of the kind of exciting prospects, especially going forward, is the idea of being able to extend and have mathematicians be able to incorporate more and more of their relative subgraph within the whole. And going forward, as more and more developments occur in the field, I hope we are able to maintain a dialogue as models and agents are advancing, and we'll be able to benefit and share in their insights. And with that, I thank you for your time.
Thank you very much, Jared. So I think now we have time for maybe one question. We're running a little bit late. So is there any question?
Hey, Jared, Pietro here. Thank you very much for your talk. It was great. I really have probably 10 questions, but I need to choose one. And maybe when do you plan to make some API access available, kind of beyond the restricted access that you have at the moment? And what kind of level of functionality and stability should users expect? What I'm supposed to do and to be able to do with Gauss.
Yeah.
Thanks.
So right now I mean, engineers are working very hard to extend functionality, and we're hoping maybe in the next month or two to extend API access more broadly. I think right now, even with beta testing, we're working out kinks, and I also think that the current workflow that we've been using of kind of human expanding and taking a given blueprint and expanding. I think this is also changing now that I think under our feet we're witnessing that models are kind of improving at the rate. So I think also maybe the mode of interaction that even this summer that we were working with has to get accommodated, and that's I think a work in progress.